Good afternoon everyone, and welcome to week 3 of your technical lecture series. We're still following the general syllabus of the branching system that you see in front of you. We looked last week in broad terms at structural physics, materials science, and structural integrity, loads and stability. We didn't cover materials technology specifically because, as I said, that is a term 2. Those are term 2 issues. What we're going to look at today is this column here, structural elements, and specifically this area, which is what we call bearing elements. So we break structural elements down into 2 fundamental areas: bearing and spanning. Bearing elements in general are the parts of a building that take load to ground. Okay, walls, columns and foundations. Spanning elements are the things that we need to hold in space, effectively floors and walls. So structural elements, spanning, as I said, we break these down into bearing elements and spanning elements, and again each of the bearing elements is again broken down into a series of classifications. Specifically walls, which again are divided into stacked walls, in other words walls that are built up of small modules that are literally stacked. Walls that are cast, such as cast concrete walls. We then look at different types of column, and we then look at foundations. I'm not sure if it's going to be in that order. When we go on to spanning elements, as I said, spanning elements are those things that are concerned with carrying floors and roofs. You might call them bridges. You might call every floor a bridge because it has to span from one bearing element to another. I tend to call them bridges or platforms or floors, if that is what you would like to call them. So, load-bearing walls, foundations and columns. Just to be clear at the outset, when we talk about walls in technical studies, we do mean a bearing wall, a load-bearing wall, something that is supporting, that is structurally supporting something else. We're not talking about partitions, and we're not talking about cladding, but you will hear people talk about walls. Oh, there's a wall between this room and that, and you will hear people talking about walls in so much as that's the wall of the outside of the building, not necessarily a supporting wall. They may well be partitions, or they may well be some kind of facade or cladding structure. This is the area that we are interested in. So let's start with those very traditional materials, brick and stone. And before I go into any detail about brick and stone, and you may think, oh gosh, that's very average kind of way of putting a building together. Yes, it is, but there's some very good reasons for it. The reasons for it traditionally were that it's something that stone certainly was the earliest building material, along with timber logs and possibly ice and possibly mud and clay. But stone is something that can be broken into smallish pieces and stacked up to form buildings of one kind or another. So stone is a very traditional building material. It's also very traditional because it's something that endures for an awful long time. So of course there are stone buildings around today that were built literally thousands of years ago. And remember, when we're talking about making good use or sustainable use of the world's resources, if you put a building together out of stone and it's going to last 1,000 years, and you put a building together out of some material that's going to last 100 years, the building that's going to be last 1,000 years is what? 10 times. You're using 10% of the world's resources that you would be if you were building in another way. Bricks, of course, are also incredibly common throughout the world. They take various shapes and sizes, but generally speaking they are designed around the size of something that a hand can pick up. It's a very simple module. It's a module. The width of a brick is the width of your hand, your thumb to your small finger, so that you can pick it up, and the weight of it, and generally speaking, is something that is manageable. So it was designed around the human scale, if you like. as I said, initially stone's been used in all sorts of fantastic ways throughout history, and in its simplest form, you can pile stone up and not even have to glue it together if you like. So dry stone walls were a common way of putting stone structures together, literally piling them. Of course, the Incas did have a fantastic ability to cut stone very accurately, and they do say that if you look closely at these stone walls, you can hardly get a cigarette paper in between two stones. The stone is still there. Of course, the roofs, which were made out of timber and possibly straw, have long gone, but the stone is still there. So still today we use dry stone walling. More often than not, we use it as a sort of cladding for buildings, or possibly for boundary walls in fields and so on and so forth. Stone blocks, clay bricks, are stacked together in a pattern, and the pattern that's stacking together is known as a bond. And mostly, in order to make a structurally load-bearing wall, the bricks or the stone are effectively glued together with something we call mortar. A mortar is a mix of cement or lime with sand in the approximate ratio of 1 of cement to 3 to 4 of sand, or 1 of lime to 3 to 4 of sand. The image that you're looking at now is a lime mortar and some very beautiful bricks. And it's interesting to think that brickwork can be, like anything in this world I suppose, can be ugly or can be beautiful, depending on the quality of the bricks, depending on the bond, depending on the skill of the craftsman that laid them, depending on the mortar and how it was applied. There are many variables, if you like, to make a beautiful brick wall. But be aware, if you like, that there are bricks and there are bricks, and there are brick walls and there are brick walls. So to make a load-bearing wall, traditionally load-bearing brick walls can carry floors up to, generally speaking, 4, 5, 6 stories high, although higher buildings have been made with load-bearing brickwork. But if you're going up that kind of height, you tend to need a brick wall which is the width of a brick, if you like. And the bonding means that you do not ever have a continuous line through the brickwork. That line is always broken up, as you can see here. So the Flemish bond, which strangely enough is very common in Great Britain, whereas the next one we'll look at, which is an English bond, is quite common on the continent, and I have no idea why that is the case. Can you see that the brick are laid in this fashion? This is a horizontal section through the wall. And so when you're looking at it straight on, you will see that's known as a header, and that is known as a stretcher. Header, stretcher, header, stretcher. Well, sometimes it varies a little bit, as in this case, but generally speaking, you get header, stretcher, and the header brick will sit above 2 stretchers. So there will never be a continuous line, vertical line through the brick bonding. Okay. Here's English bond. You'll get a course. So that's a course, a continuous course of bricks. So that's another course. You'll get a course of headers, and you'll get a course of stretchers. And again, you'll see that it's important that line is never continuous. It's always broken up through the structure. Okay. In old money, that's called a 9-inch wall. Bricks are about 260, 70 mil, I think. American bricks tend to be 300 mil, but it was 9 inches by 4.5 inches. So traditionally that's 4.5, and that's 9 inches long. Okay. Just to confuse the issue, I would have said to you that every time you see a wall that's just a series of stretchers, not headers, it's going to be a thin wall, isn't it? It's going to be a 4-inch wall, 4.5-inch wall. It's just going to be one thin wall, and therefore it will not be load bearing. It'll just be a facade, if you like, something that's keeping the rain and water out, and the floors are actually being carried by some other system, concrete or steel, what have you. Nevertheless, the problem with bricks, which is the same as the problem with stone, which is the same as the problem with concrete, is that these are all very dense materials, and we will talk about this at some later stage. The density means that their ability to stop heat or cold passing through them is virtually nil. So they allow heat and cold to pass through them. They do not make for a well insulated building. It was discovered that the best insulator, of course, of all is air. So if you build two thin courses of brickwork and have an air gap in between them, you're building a cavity wall. Now structurally that wall works because every so often they are tied together with little metal ties, these two walls. You can't see them anymore. So when you look at a wall on the outside and you see that, if it's a fairly low building, say 3 or 4 floors high, and this will be true throughout the world, and you just see that, you can be fairly sure that actually it is a load-bearing wall. It's a cavity brick wall. If you see a building that's sort of 10 floors high or bigger and you see that, you can be absolutely 100% sure that it's not a load-bearing wall and it's just a facade. Here's an example of a very typical cavity wall. So there's bricks on the outside, because that's something. On the inner skin is not bricks in that case. It's actually a lightweight aggregate sort of block work. That's 3 bricks high. It's cheaper and easier and quicker to put together. There's the air gap, and actually in this case it's got this, it's got this fibrous material which adds to the insulating quality of the wall. The inner face will then be lined with something else beautiful to make it acceptable on the inside, if you like. Let's have a look at a few astonishing brick buildings, again just to emphasize the fact that although you think of it as a very common and simple material, it can also be very beautiful and very dramatic when used well by architects who know what they're doing. These are very, what should we say, monumental, monolithic buildings, aren't they? They do have a very particular kind of quality. They are church-like. But for many people, the proportioning, as well as the fact that they are monumental, and the fact that they're made of very, very tiny modules. But those tiny modules make this astonishingly monolithic structure, gives it a fantastic quality. This is an architect who I will mention over and over again, whose name is Eladio Diesti, D-I-E-S-T. He's a Uruguayan architect, and this is one of his buildings. It looks frivolous. It's a kind of, it looks almost as if you've taken a lump of clay and just sort of punched it or dropped it and to make a kind of funny random wall. It looks very organic. But of course, think about this wall. It's actually, because it's folded, because it's doing that, it gives it an enormous amount of structural stability. Diesti was very clever. He was a structural engineer as well as an architect, and he was thinking about that. He made some fantastic roofs that we will look at later on using the same process. As it happens, again, going back to this issue of making good use of the world's resources, Diesti came from Uruguay. There wasn't a lot going on architecturally until he came on the scene, and he thought to himself, what have we got a lot of in this country and what are we not making the most use of? Of course it was clay. So they started quarrying clay and making bricks, and Diesti thought, what can I do with bricks that is fantastic? Again, the brickwork can be very beautiful according to how you detail it, how you deal with it. So this is actually, oh God, I've forgotten his name. It's Berlin. It'll come to me in a minute, or it may not. You'll have to get back to me on that one. Beautiful building. The point, if you like, the mortar beds in between the bricks. So we're using a very light coloured brick, aren't we? But we're also using a very light coloured mortar bed, so it almost becomes a homogeneous, simple homogeneous surface, which is rather lovely. So this is a modern cathedral. Sorry, it's a slightly blurry image. Actually, it's a modern church, I beg your pardon. It was built in Warwick only about, I'd say about 10-15 years ago. Just to show you that, you know, we can still do, if you like, what the great Gothic builders, masons, built, understanding their processes. In this case, what we're looking at here is actually a brick. This is a brick column, so these are a series of columns, and of course they are very massive because I remind you again that brick and stone and concrete without any reinforcing have no tensile strength. They're very good in compression. You can push them down very hard, but they will pop, if you like, or explode under a huge amount of pressure unless you make them massive enough. So these are massive columns, as were all the great cathedrals in the world, of course. So here we have a brick core, and we have beautiful cut stone, if you like, cladding to the brick core, but the two are acting together structurally, so that becomes structurally one large column. A lot of these are now cut by machine, laser cut in fact, and when we look next semester at stone in more detail, we will go into that a little bit more. So those were walls, load-bearing walls, that were made from small modules, smallish modules piled up together, generally stone blocks or clay. Of course, bearing walls can also be continuous structures, so let's look at reinforced concrete. Concrete, along with a few other materials, is one of those materials that is formless until it's poured into some kind of mold or something that will then give it its form. And we call that formwork with concrete. We call it formwork because it gives it its form. What you're looking at here is a very simple container into which the concrete will be poured. But you will notice in here that there's some little steel rods. Now it's actually a cage of steel. That's the reinforcing. That's the steel reinforcing for the concrete, which is placed in first. Now it's tied together, of course, but when you pour the massive concrete in here, the weight of it is going to be pushing on this is a very simple timber shuttering. It will be pushing on them, so we have to tie it together to stop that timber shuttering failing, don't we? There it is once it's been poured. Modern shuttering takes all sorts of shapes and forms. The sort of shuttering that's used, we're looking at here, is steel, which can be reused. You pour the concrete into it, you can take it away and reuse it. With timber, in the old days when we used much more timber shuttering, and we still do in various parts of the world, the timber, once it's been used, tends to be discarded, so it's not very efficient. Here we are pouring into. In fact, in this case, the shuttering is a kind of it's a kind of insulating material, which is interesting. Concrete, when you take the shuttering away, tends to take the imprint of whatever the shuttering was. And again, we'll go into that in more detail when we look at concrete. But what you're looking at here's the rebars, here's the steel reinforcing inside the concrete. This is a load-bearing concrete wall, and it's very shiny, isn't it? It's very shiny, very beautifully polished. So this is actually it's a kind of concrete which is called self-compacting concrete. Again, I'm not going to go into a lot of detail about concrete, but suffice to say that when you pour it, you have to get the air out of it. You pour it into a mold, you have to get, there's air when you're pouring concrete. To get the air out of it, concrete is actually vibrated to suck the air out. Self-compacting concrete sort of does that. There's certain additives, chemical additives, that do it all by itself, so you get this beautiful shiny finish. Now, just to remind you, the building that you're in, or you would be in if it was appropriate at the moment, and I'm not sure if you're in the building or not, is built of a series of reinforced concrete load-bearing walls. We call them shear walls. They're actually lateral walls. It is these that cut across the building. So there are, in fact, there's an end wall, 1, 2, 3. I think there's a couple in there. 4, let's call that. 5, 6, another one through there. 7, 8, 9 at that end, and that's the fire escape. So there might be a little cantilevered section here. That's us, as you know. Well, you don't know. That's our office. That's where Will and I are. So we've got a series of all the floors, everything that's going on in here is taking its load back to ground through this series of, did we say 9 shear walls? All the loads are going back down to here. So everything that connects in between is a series of bridges. In fact, there are literally bridges, because you're walking, if you're on the top floor here, on the 5th floor, you're walking along a bridge that connects this wall to this wall, and then there's a series of slightly smaller bridges that are cantilevering out in this case, and so there's a kind of hierarchy of structure. Again, if you don't, you may or may not know the building well now, but this is towards the rear of it. This is a fire escape. You know, on the one hand side, it looks okay. It's a simple structure, but it's the simplicity of it actually that gives it a great deal of elegance. It's a very simple planar reinforced concrete wall here, reinforced concrete wall here. That is doing exactly what it has to do, which is the staircase, which is coming down to ground. But all the load is taken by these two big sheer concrete walls. And just a reminder again, whenever we mention concrete, we mean reinforced concrete. Concrete on its own will only work in compression, in pure compression. The great ability of concrete to span in all sorts of directions, as columns, as floors, as walls, as pretty much anything you like, is because it's reinforced with steel. And very often the mass of steel in concrete weighs the same as the concrete itself. Now, what are we looking at here? Here's a reinforced concrete wall. And remember when I said the formwork that the concrete is cast into, the concrete will take the imprint. Now, in this case, of course, the formwork was a series of timber planks. And when you take that away, you've sort of got what almost looks like a timber wall. But of course, it's not. It's the imprint of the timber planks on the concrete. If you were all in the room now, I would ask the question, who of you can tell me why? What are these little holes? What are these? What's going on here? And most of you would hazard some funny guesses, but anyway, what are they? They are the result of the fact that, as I said earlier, you have to tie one side of the formwork, the shuttering is another word for it, you have to tie one side of it through to the other side to stop it falling away when you pour the mass of the concrete into it. This is the result of that. Now here, what the architect's done is, yes, he's plugged it a little bit, of course, but he's allowed it to be visible. And he's allowed this line to be visible too, because you can't cast an enormous great concrete wall in one go, because the weight will become so heavy on the bottom here that it will begin to fail when you're casting it. So you cast concrete walls in sections. So that was done one day, a few days later that was done, and so on. So the architect, by leaving these little clues, is actually telling us how the wall was built. And we do like this. There's a kind of honesty to it, if you like, about the process of building the wall is visible in the final result. That's the South Bank of London, monolithic concrete. There are other kinds of, shall we say, monolithic load-bearing walls. Normally, what we call laminates. Now, laminates are when we layer materials together, where we layer thin panels of materials together, and that layering of materials, that build up, if you like, begins to give strength to the material. Some of you might know what a piece of plywood is. Think of a simple plywood sheet. It actually is quite stiff and strong, can take load vertically onto it. It's because it's a layering of materials. Now again, this is something we'll talk about when we look more closely at wood later on, but generally speaking, most wood that's used in construction industry now is known as engineered timber. It's not timber that comes straight off a tree. It's not just sawn off a log, if you like. It is manufactured by small sections. This particular process is called cross-laminated timber. So the timber, if you remember, well, you don't remember, timber has a kind of grain, a directionality. So if you laminate one layer in one direction, you laminate another layer in the other direction, and so on, you build up a very strong piece of timber. So these are load-bearing walls, modern load-bearing walls. Here's an interesting laminate, because we've got some kind of fairly simple what's called oriented strand board. That's a particle board, artificial timber board. This has been laminated or glued, if you can see, over a foam core. There's a foam core that gives it a certain thickness, certain dimensionality. The foam also acts as an insulator. Remember, we saw that earlier on, because there's actually lots of tiny air bubbles trapped inside there. So this laminating process of timber, foam, timber, creates a very stiff panel which also is insulative, and it's exactly the same process. Again, we will be looking at this at some stage, that's used for plastic buildings, fiberglass, fiber reinforced plastic buildings. Believe it or not, we've reached the stage where we understand enough about structural glass or structural glass technology that glass itself can become a load-bearing wall. This really is state-of-the-art. Well, it's actually a few years old now, this particular house, which again, I'm sorry I can't remember, but I will give you the reference at some later stage. So the roof that you're looking at here is being carried on this wall. There are no columns, you can sort of see inside there. There's nothing else going on. The wall is carrying the roof. It's a load-bearing wall. It's a laminate, again. It's a series of layers of glass bonded together to give it thickness and strength. It's been toughened in a very particular way, which again we will go into at some later stage, but there it is. A structural glass load-bearing wall. The last thing we're going to look at in this lecture is foundations. I think I mentioned to those of you who heard the introductory lecture that we do need to understand foundations, even if we do not need to specify them in any great detail. And when I say understand them, you can see here there's a list of 4 different types: strip foundations, raft, pad and pile. What we need to do as architects at the very least is appreciate the kind of foundation, the type of foundation that we're going to need for the type of building that we're designing. We may not know how deep the piles go, we may not know how deep the strip foundation is, but we do need to have some kind of approximation, and because all of these are determined by, on the one hand side, the type of building that's going on top, the size of it, the kind of construction technology you're using, and of course on the other hand the type of terrain into which it is being inserted. The tree is of course a kind of icon because it has this incredible strength from the fact that the rooting of the tree has a particular way of engaging with the soil underneath it. If you want to put a tree on a building, for example, and often students do make this mistake, they design a building, they design a roof, and they say, wouldn't it be nice to have trees on the roof? Try and remember that whatever you're looking at up here is exactly the same as whatever you're going to be looking at underneath. There's an enormous amount going on underground, as much as there is the canopy, the roots and the canopy mirror each other. It has to spread its roots far and wide for stability purposes. It has to root them deep into the ground for anchoring purposes. Okay. If you, going back to what we were looking at earlier, if you do have a continuous load-bearing wall, and let me remind you again that the building that we're in, the campus of Marylebone Road, which is 6 floors at the most, that building has the continuous reinforced concrete walls supporting it. They will be supported on a continuous foundation known as a strip foundation. The foundation is continuous because the wall is continuous. The loads are carried continually all the way along the length of the foundation. So we're digging a trench, we're pouring, in this case again, reinforced concrete into that trench to carry the load of the building. So pretty much any small-scale structure that has continuous load-bearing walls, brick buildings for an example, will normally have strip foundations. Traditionally, again, the foundations tend to be concrete or reinforced. I should say reinforced concrete because always, as I said, concrete is reinforced. More traditionally, there would have been crushed stone of some kind or another, or even bricks would be used to support the load-bearing walls. For many buildings, you'll find a raft foundation, and a raft is a continuous, again, reinforced concrete floor that's poured onto the ground. The reasons for a raft are twofold. One is that, of course, you can now take load pretty much anywhere onto this. You don't have to just follow the line of the strip, do you? So if you wanted a column here, you want a bit of load-bearing wall here. If you want a kind of variation thing. It's a kind of easy way of taking load back to ground. The other reason for raft foundation is if you have any kind of instability at ground level, okay, if the ground is likely to move in any way or you're not sure about it, it does act as a raft. So it's a continuous, if you like, floats on the surface. So if there's any movement underneath, you know that at least this as a whole will remain homogeneous and will not move. There, just to remind you that the amount of steel reinforcing that will go into a raft foundation. It's an enormous amount of steel. For lightweight low-rise structures that are built on columns of some kind or another, or some kind of post and beam structure, such as this lovely little timber building, which is an architectural association building actually. This is landing on these just little pads. They're called pads. So the concrete, these pads probably go into the ground not much more than a meter, I would say. Probably about a cubic meter of concrete on each of them. They're proud of the ground, which is quite nice. Again, that's a nice detail because we know that timber doesn't like to get wet, does it? So we don't want, or at least not saturated, so we don't want the timber touching the ground. So they're just proud, allowing the timber to connect just above the ground. Here we are again, little concrete pads for low-rise simple structures. Whoops, I'm doing something silly. Cancel that. Help. Yeah, sorry. So I use that expression again. This is for point. So pads we use for point loads onto the ground. Okay, rather than a continuous strip. When we have point loads, we're taking it down. And of course, in a way, you're using a lot less concrete. We're using a lot less concrete than you are building a strip foundation. You're using a lot less than if you're building, certainly a lot less than you're building a raft. So in that way, it's an energy efficient way of putting a building together. Little pads. If you've got a medium to high-rise structure, and the pad will not take the mass that's above it, you will use piles. And mostly the pile, even though the pile will then possibly be continuous with a column, mostly you will cap the pile with a kind of reinforced concrete bridge, and then you can again place the columns anywhere along that pile cap. In a way, what you're doing here is you're building a continuous strip foundation along the top of a series of deep pads. So you're sort of combining all the principles in one. Now there are really only two types of pad. And one is the type of pad where you bore down to the fact where you have bedrock. You have a hard, you reach something, you can bore down far enough where you can reach bedrock, and that will support the load of the structure. If the bedrock is either too deep or you actually don't know where it is, which is often the case, you will use these kind of piles, which are called friction piles, and they will have designed in such a way that they will not sink down into whatever the substrata is, because the edge is slightly fritted so that it will not fall into the structure, into the earth below. Generally speaking, to make piles you need to excavate quite a lot of earth. That's the process. Again, look, this is the steel. That's the steel reinforcing, which will knit into the columns that will go above. Just to give you some idea of the amount of piling that does go on under many structures in this world. This is actually on the south bank of London. There is a kind of lightweight pile, and this is it, or if you like, a slightly more simple way of achieving the pile. They're called helical piles, and they are, or screw piles, sometimes called. They can be put into ground at a kind of fairly soft ground, fairly quickly, fairly efficiently, not very huge, not very heavy. So even for fairly lightweight structures, where you have point loads, say lightweight timber building, for example, a helical pile could well be your solution. And here it is, just carrying this just nice little timber structure here being carried again with these shoes, these metal shoes, proud of the ground again, because we don't want the timber touching the ground, do we? So we could be getting towards the end here of this. I just do want to mention this structure only because it's well, like a number of structures you'll find that have been built throughout history, that there's an importance to them in engineering terms that is enduring, shall we say. This is the Bell Rock Lighthouse, which is off the east coast of Scotland, and it was built by a man named Stevenson, who in the English world is known. His son was known better than he was. His son was named Robert Louis, who wrote a book called Treasure Island. But most of the family were engineers. Stevenson was actually an iron worker, metal worker, in I think Glasgow or Edinburgh. I apologise for not knowing. Will McLean will have my guts for that, but never mind. And it was at a time, this is about 200 years ago, when throughout Europe they were losing an awful lot of trade, an awful lot of ships, and an awful lot of men because of the rocky outcrops around European shores. A lot of ships were sinking badly. It was very sad, and they were desperately in need of some kind of beacons in order to solve this problem. This required two things. This required structural innovation and, of course, optical innovation. It was the French that developed these astonishing, I think they're Fresnel lenses that could cast beams of light many, many miles, or a long way anyway. They solved one part of the problem. Stevenson solved the other part, which is building these beautiful stone structures. This particular lighthouse, the Bell Rock, this rock is underwater for 6 months of the year. So they had to build the lighthouse in 6 months, and they had to build it. This is before there was any kind of automated power, no cranes or anything like that, just men and horses and boats. So there it is for half of the year. And what he did was they built it there. You can see here there's a temporary structure on the right. They built a timber structure for the workers, and the workers started hammering away at the rock to make a foundation for the structure. So this is load-bearing stone building, as you can see, and it tapers, of course, because the mass, you need heavier mass down here, gets thinner and thinner as it rises. The other thing they discovered when they were experimenting with the lateral load of waves against the structure excuse me, and they did this by making physical models and throwing buckets of water at them, they discovered, which you'll find quite often in structure, that this curve was a piece of pure geometry. It's a parabola, hyperbolic parabola. Parabolic curve, beg your pardon. The parabolic curve turned out to be the most efficient curve to resist wave impact. But the other thing they did to resist wave impact, now this is a cross section through the foundations. So these are stones. So down at this level here, it's a continuous stone circle, isn't it, down here, and then it starts to break up as you go up through the structure. So they cut the stones a bit like a jigsaw, as you can see, to interlock with each other, so any impact, any wave impact, would be resisted by this astonishingly beautiful array of stone. You're also looking at, they were doweled, so anybody knows anything about joinery or timber work, that vertically these are little timber dowels are inserted and hammered through from one course to the other. This is for taking bigger timber structures for other reasons, for floors and so on. So to get back to foundations, what we were talking about, the other half, if you like, of foundations, of taking load to ground, is that of course very often we have to excavate, or we want to dig, or we want to make basements, or we want to go underground for one reason or another, and when we do that we have to stop the earth around it from falling into the ground, and to do that we build what's known as retaining walls. And again, there's a number of ways in which we can do that. This is a fairly common way, again, throughout the world. It does use reinforced concrete, and what you can see what's going on here is that there's a series of effectively reinforced concrete columns. So we're boring a series of holes right next to each other, pouring concrete into those holes, reinforced again, still reinforced concrete, That's the cap. So it's a series of piles. There's a concrete pile cap. Having done all that, we then excavate. Then we take the earth out from underneath. So we start by, if you like, perforating the ground with this series of holes and concrete columns, and then you take away the earth from underneath. And then you might put some kind of cage onto the surface. You'll probably spray concrete onto that to give it a nice finish. And you can either then build out of this hole here, take the load back down into here. You might again even have piles or pads, or even a strip foundation down here. Or if you want to, of course, you can build straight off that retaining wall. You can build off that pile cap, can't you? Here's an example of it underground. Often nowadays in construction sites you will find that they're going down at the same time as they're going up. So by boring this, here's the secant pile wall. By boring that wall, they can start building up off it while they're excavating underneath it to save time. Here's another type, again very common. It's called sheet piles, and it's steel. As you can see, steel sections. This crinkliness we'll find over and over again in structure, that this corrugation, this bending or folding of structure, gives stiffness and strength because it's giving depth to the structure. These kind of these kind of walls, these are actually, rather than cast or poured as the concrete columns where we saw earlier, these are actually hammered into the ground, so they're also quite useful for water retaining. So if you need to make a dry dock, or if you need to make a harbour of some kind, you suck the water out. That's what these sheet pile walls are often used for. They can often be used as temporary structures, but then they're sometimes left permanently. Now here's an example of, you're holding back here a canal. This is in Berlin, as it happens. That's the Neuss Museum in Berlin. So there's a secant pile wall holding back the water. This is a slightly more modern way of building a retaining wall. They're called gabion walls, as you can see. It's a cage of stone, stones of certain aggregates. All sorts of different shapes and sizes can be used. And of course you have to do the excavation. There's a certain sequence to it, and then you pile up these cages of stone. As in anything in architecture and design, it's an art. There's an art going on here. This is this caging here is very much the sort of structure that you will find when you're looking at reinforced concrete, reinforcing for concrete, or as Americans call them, rebars. There are, if you like, tradesmen all over the world who specialize in doing nothing but making the cages for reinforced concrete or making the cages for gabion walls. There are particular tools and there are particular techniques. On very large scale heavy-duty civil engineering, where you have to make a retaining wall, we use what's known as a diaphragm wall. So here, instead of just pouring columns into casting a series of piles, if you like, into the ground, we're casting huge slabs of reinforced concrete in sections into the wall. So how are we getting on for time? I don't know. Columns. Now, the diagram that you're looking at is a kind of idealized, if you like, medium-rise building. Of course, in the real world, we don't build buildings like this. We tend to build them with columns of the same cross-section right the way through. But if you look at the bottom, what you'll see is a little kind of rule of thumb, if you like. And this rule of thumb applies, it doesn't matter what material you're building your columns from, it applies right the way through, pretty much roughly. So let's look at this. At the top, we've got, imagine none of this was here, we've got a single story building. And sorry, but I should remind you, this is an 8 meter grid, which is sort of grid that structural engineers tend to work on. So on plan, imagine a grid of 8 meter squares. Okay, that's an approximation. If you double that, if it's 16 meters, you have to double the column, and so on. If you halve it, you halve the cross section of the column. But we're working on 8 meters. So for a one-story building with 8 meter spans, we're looking at roughly 1 foot by 1 foot, 300 mil by 300 mil. Okay. For the next what have we got? We've got now 1, 2, 3, 4, 5. We've now got a 6-story building. Let's say it starts here. Here we're looking at 700 by 700 mil cross-section column, okay, carrying the load there, and so on. So the columns are getting larger as we go down, which makes sense because at this point we're only carrying 1 floor. At this point we're carrying 6 floors. At this point we're carrying all the floors above. As I said, in the real world, just due to construction technology efficiency and other reasons, they tend to build the whole structure with the larger scale columns. But that would be an idealized thing. So that could be useful to you in the future. If you've got stone, as I said earlier on, or brick, clay, and no tensile strength, no reinforcing, no tensile strength in the material, you need an awful lot of mass. You need big, heavy columns. Interestingly, and I'm not sure whether I go into the order of the classical order of columns. I might briefly go into it if you're interested. It's a proportioning, again the height to cross section. These are, oh yeah, I do. No, I won't go into that now. Just to note that they were proportioned roughly on the human body, I believe. I won't go into this now, but you can look at it. You can come back later, because when your tutor says to you, are you going for Ionic or Doric, you can explain which and why. Okay. These are stone columns at Durham Cathedral, and they're, I will get onto it later, onto Gothic architecture. For many architects, in terms of the construction technology, in terms of what was known about engineering at the time, these cathedrals throughout the world are the epitome of what could be achieved structurally with the material available. But just interestingly, I've realized I can't really explain this very well now, but the columns here, again, there's always this ratio of the cross section to the height of the column. How high can it go according to the cross section? If you took a square piece of paper and you folded it round to make it into a tube, and one end met the other end, you would find that that is the exact proportion of these columns at Durham Cathedral. Very beautiful things. Don't think that a column is just a simple tube or a simple square. That's Sagrada Familia. That's more Gaudi raking his columns at funny angles. That's Le Corbusier, Villa Savoye. These are actually steel cylinders with concrete poured inside of them. That's is it Mies or Frank Lloyd Wright? Oh God, somebody's going to do me in. Victoria. Anyway, one or t'other. Again, don't be deluded. These are square section steel columns. It looks very simple. It is very simple, but the detail, in order to make it simple, how the glass meets the columns, the fact that it's sat just gently off the ground, that's one platform coming down. All of it, I can't eulogize enough about the beauty of this building and how hard it is to achieve what seems very minimal. These are aluminium columns. So now we've got a lot of them, and they're very small. It's almost the antithesis of the Parthenon, isn't it? Tiny sections, small sections, and again, look, they are not all perfectly vertical. Now, again, that's not. It's a bit of fun, but it's not just a bit of fun. What's it doing? The moment you start to give any hint of triangulation, of course, you're stabilizing the structure against any kind of lateral load. So that those ones that are raked, we call it raked, R-A-K-E-D, slightly not quite vertical, are actually working structurally. There's more raked columns. That's Willie Alsop's building on the south bank of London. These are extremely raked columns. Is it Richard Rogers or Foster at Madrid Airport? And look, here's the foundations. Ooh, isn't that nice? Lovely detail. They're coming, they're visible, if you like. These are probably concrete. They're probably piles that will go down into the ground, or at least that will arrive somewhere like that, and then there'll be piles underneath that. And they're proud of the ground, and there's the steel connection there, and there's the steel connection at the roof. Very lovely. There's concrete being used. That is Mies van der Rohe. That roof, again, we'll look at that later when we're actually looking at spanning elements, probably next week. This whole entire roof is just being held on the perimeter here by 2, 4, 6, 8 columns. Okay, and again, these are, we can see them here. It's not just square section, is it? It's actually a cruciform, and the fact that it's a cruciform on plan means that if you remember talking about pinwheel structures earlier on, that everything is resisted in all directions, isn't it? It's resisted in that direction, it's resisted in the other direction, but it also tapers. And look at the connection point. Beautiful, because all the load comes down to just there, just that point there. The mass, all that mass just connects at that point there. Okay, very beautiful. Look at these lattice. This is a truss, isn't it? Column as a truss. Very beautiful. I think this is Nervi, Pier Luigi Nervi, and it is worth looking at these because they are, again, somebody might say to you at some point in your career, oh, we want you to design a warehouse, and you're going to say, oh really, is that the best gig I can get? I say, well, there's warehouses and there's warehouses, and this is Nervi's take on a warehouse. Absolutely beautiful building. All it's doing is containing whatever it has to contain. It's an industrial building, isn't it? But it's a series of umbrellas in a way that's keeping the rain off and the wind off. And the umbrellas are concrete columns with steel girders, tape coming out from from that central point there. You might notice also that the columns are tapering, as I said before, okay, because the mass is growing, isn't it? It's getting heavier and heavier as it comes down. They're cruciform on plan here, but by the time you get up here, they're circles. So it's morphing, if you like. It's in-betweening from the cruciform to the circle, because at this point you need the circle in order to deal with this array that's cantilevering off. Now, each one of these will work structurally on its own, won't it? As I said, it works like an umbrella. That's fine. That's fine as a structure. So what else? What else has he done? He's allowed natural light to penetrate, so they actually don't touch. This is glass. I'm going to allow natural light to penetrate in between the umbrellas and give this beautiful lines through the structure, these grid lines. And of course, even at the point where the steel meets the circle, he's allowing some light to penetrate, some glass. Can you see here? There's the circle. There it is gradually morphing. Of course, it was built in a series of sections. This is reinforced concrete column. Pier Luigi Nervi, Nervi. Thank you very much. Good night. See you next week.